Welcome to Lab 5, Quantum Mechanical Tunneling. In this lab, you will be characterizing a rubber-nickel compound called Quantum Tunneling Composite, or QTC. You will be using it to make a touchpad. This lab requires the use of a 5-volt high-current power supply. Let's go over the additional components. For this lab, you will need copper tape, double-sided tape, 3 glass slides and 1 glass slide coated with ITO, about 5 pieces of the QTC material, some ball bearings, rubber strips which act as spacers, binder clips, some tweezers, 2 pieces of glass coated with copper. These act as electrodes, a sensitive displacement gauge, finally some alligator clips, and a multimeter. For part 1 of the lab, you will be measuring the displacement versus resistance curve of the QTC pill. Begin by placing a copper electrode on the table and attaching it with double-sided tape. Place the QTC pill between the 2 copper electrodes and hold it in place. Set your multimeter to measure resistance and connect it to the top and bottom electrodes. Now position the displacement gauge on top of the QTC pill, which is sandwiched between the electrodes. You can now measure the resistance of the QTC pill as you press down on the displacement gauge. Here's the same setup from the side view. As displacement or compression increases, resistance should decrease nonlinearly. This should make a straight line on the log-log scale. Part 2 of the lab will be measuring the IV characteristics of a QTC pill. We will use 2 glass slides to make a more advanced pair of electrodes. Begin by covering 1 glass slide entirely with copper tape. Attach a 3rd piece of copper tape as shown in the lab handout. With the 2nd piece of glass, attach a single piece of copper tape orthogonally. Place the QTC pill near the center of the glass slide so it makes good contact with both pieces of copper. Add rubber strips for spacers. Finally, finish your setup by adding binder clips. Here's a close-up of the finished assembly. Connect the power supply. Connect the multimeter in series so that it can be used to measure current as you apply different voltages across the QTC pill. Here's the same setup from the side. The power supply is connected to the input of the multimeter, right now acting as an ammeter. The output from the multimeter is connected to the input of the QTC assembly. Finally, the QTC assembly is grounded to the ground of the power supply. Because we do not want to keep current across the QTC for long periods of time, we will begin by opening the circuit. To make an IV measurement, first set the power supply to the desired voltage, connect the circuit briefly, and take the reading from the multimeter. Repeat this for each voltage documented in your lab handout. Take IV curves for different biases by adjusting the positions of the binder clips. Now you will make your very own touchpad. The bottom half of the assembly has an electrode that's identical to what is made in part 2. Place copper tape on one of the glass slides. Add a third piece of tape to make it easy to attach the alligator clips. The top half of the assembly will be made using a piece of ITO coated glass. The side of the glass with ITO should be marked, but if you're unsure, you can always test this with the ohm meter. Place 2 pieces of copper tape as detailed in the lab handout. Now put 4 rubber strips to act as spacers. Then place 4 pieces of QTC pills in the 4 quadrants of the slide. You will put ball bearings on these QTC pills later on. So use a pen to make indents on each of the pills to hold the ball bearings in place. The tricky part is the placement of the ball bearings, but after a few tries, you will get the hang of this. Flip over the top glass slide so the ITO makes contact with the ball bearings. Secure the assembly using alligator clips. Here is a close-up of the finished touchpad. Finally, characterize your touchpad by connecting it to the multimeter. Use the multimeter to measure the resistance as you compress the touchpad near and far away from each pair of terminals. Do this in both the vertical and horizontal directions.